Yeah, thank you very much. So I'm going to talk about work done at Aalto University here in Finland. It's mainly experimental work on heat transport in superconducting circuits, and it is the work is, in fact, it is done in my research group, which is part of the Center of Excellence here in Finland, which is a program which is running here for 8 years, and it consists of 11 PIs, mostly people working on quantum circuits. Several of us are working on superconducting systems. We have people from Aalto University, we have people from University of Helsinki, and quite importantly, we also have people from ETT, which is the Technical Research Center in Finland. So we have kind of very basic research and also applications here. So let me go to the actual topic. So the outline for what I'm going to tell you today is that I'm essentially talking about systems where we have either 1 or 2 heat baths, and in the first part I will tell you about how heat is transported between 2 baths that are in our case formed of electrical resistors on electrons in electrical electron reservoirs on a chip, and usually the quantum system is a superconducting qubit. Second part which I talk about is about calorimetry, so it's very related to this. So how to detect very tiny amounts of energy in a similar setup by measuring temperatures of these let's say mesoscopic heat baths. And the last part is a very recent work on which is a little bit more classical, so that's about frequency to power conversion, and I will tell later on what it really means. So let's start from this.
Pekola, sorry, is it we are still seeing the first slide? I mean, I'm not sure whether it's everyone or it's me only.
Yeah. There's a problem. I don't know why. So maybe, yeah, let me. Can you see it now?
Yeah, now
yes. Now yes.
Okay. So this is the story about the first slide where I was telling about our center. So it's about these 11 research groups, and I will not go back to explain what I said, but this is indeed the team, mainly from Aalto and VTT and University of Helsinki. And then these 3 topics. So it's essentially heat transport between mesoscopic heat baths, which will be clear in the later what I mean by them, and then about calorimetry and recent work on frequency to power conversion. So let's start from this first one, which is in fact quite related to the second one also. So in the first topic, what we are doing is that we are looking at essentially thermal conductance through this quantum systems, and as a reminder for people, so already in the 1980s it was there was a set of experiments. Of course, this was backed by a lot of theories that electrical conductance in a ballistic contact will be quantized in units of E squared over H, and that was something which was realized at that time in semiconducting constrictions, ballistic ones, and at the same time it was already earlier it was predicted that thermal conductance relates to this electrical conductance essentially by Wiedemann-Franz law, so that you have also sort of thermal conductance quantum, which is related by this Lorentz number to the electrical conductance quantum. So this is something that was then realized in the experiments, in several experiments. In fact, for electrons, most maybe more recently in the experiments in Paris in this or again in the quantum Hall regime, but in the semiconducting electron systems, where people could see that indeed the thermal conductance as well is quantized. And the pioneering experiment is proof that this thing is not only specific for electrons and not only for fermion systems, was done on phonons by people like Keith Schwab and Michael Rukes already 20 years ago or so. So where they could see that thermal conductance is quantized. And this is the kind of the name of the game. So you really have this kind of quantized thermal conductance, which applies to any types of carriers in principle. So we have a recent review about this, a colloquium type review with my student Bayan Karimi on this in RMP. So as I said, it should apply for any types of carriers. So what we are in fact after is how it applies for photons. So not only phonons on solid, but also for photons, and in particular, in our case, for microwave photons. So what we mean by this is that if we take, for instance, this setup of Johnson and Nyquist, where you have two resistors which are seeing each other, there is no usual kind of diffusive thermal conduction between them, but they both produce their thermal noise, which then, of course, creates some sort of currents in the circuit that you see here. And by a very simple calculation, you find out that if you include the thermal noise, include the frequency-dependent thermal noise, the quantum noise as well, so then what you obtain is that the power that is transmitted between these two resistors is given by this very simple expression here, where the power depends on the difference in the second powers of the two temperatures. And the prefactor here, in fact, with simple algebra, you find out that it leads to thermal conductance for small temperature differences, which is the quantum, exactly this quantum of thermal conductance. And the prefactor here, this small r, which modulates sort of this, is a kind of a matching factor which assumes value unity when the two resistors are equal. So would one measure such things? In general, measuring heat currents, I will give now you a short kind of the toolbox of how these kind of measurements are done. So what we do is we measure heat by having these two different heat baths that I was already explaining to you. They are not full heat baths in the sense that they have finite heat capacity, but they represent, in our case, usually a large number of electrons, like 1 billion of electrons or so. And if you heat one of these things to a different temperature from the other, you will see that there is a heat current, of course, running through the system. First of all, it runs through to the underlying phonon system by the electron-phonon coupling, but it also runs by this photonic type of heat conduction between the two resistors. So by just simple continuity equation, you can see here that if you know the thermal conductance between electron and phonons, which is in fact the case, then you can really determine how much heat is transported between the two and determine this kind of a thermal conductance. So this is the way that the experimentalists measure heat currents in the measurement. So what is an important ingredient here is naturally the thermometer. And what we typically use for a thermometer is just a simple tunnel probe, so like doing like tunnel spectroscopy. So the electrical current through a tunnel junction, which is sandwiched between two different types of conductors. In this case, this normal metal, this is our object of interest here with this Fermi distribution of electrons, and this is our temperature, naturally this width of this distribution. If you connect it to a superconductor, then you will have very strongly temperature dependent current voltage characteristics of this junction, and it is captured by this simple Landauer-Büttiger type of expression here, where the only temperature dependent thing is the distribution of electrons in this normal conductor. And here we have the temperature independent density of states of a superconductor. So this yields us a very nice local probe of temperature on this mesoscopic heat baths, which there's an example here, one metallic island with 3 micrometer length and with a lot of superconducting probes connected to it.
So
another important
question.
Yes.
So you measure this dynamically in time? Like, can you see how the flux changes in time?
So let's say in the first part of the experiments, we are looking at stationary effects. But yeah, this is a very good question. So we usually, recently we have gone into the experiments where we can do it in a temporal fashion. So we can measure it at rates of up to maybe one microsecond with 1 microsecond time resolution at best. So, but what I show first is just a stationary experiments where a simple DC characteristics is enough.
I see. Thank you.
So so the other ingredient that I had to tell you is that is this electron-phonon coupling, which is kind of already very well known and charted property of usual metals. So the thermal conductance between this electron system to the heat bath, which is the phonons, is given by the current between the two is given by a difference in the 5th powers of the two temperatures, and this leads to the thermal conductance, which is proportional to the 4th power in temperature. And all these parameters here are known very well for the materials that we use in the experiment. So V is the volume of your absorber here, and sigma is the material constant, which is in fact very well known, for instance, for copper that we use in the experiments. Okay, so this is and then there's another ingredient. In order to do such measurements, you also have to kind of control the temperatures in your system. So if you have the two paths, you want to control one and measure the other typically. And how you do the control of the temperature is that you apply kind of joule power to one of these resistors there. And we don't apply a simple joule power. We use this kind of a NIS tunnel contact there. And this gives us kind of a very non-monotonic feature. So in fact, if you put a small bias voltage to this conductor, then what happens is that you are just skimming off the hot electrons from the normal conductor. And this leads to the cooling of the electrons in this. So the power that you really inject to the normal metal here or power that you draw from the normal metal is first, it is positive until you bias the contact up to the gap of the superconductor. Thereafter, it becomes essentially the typical usual joule power, where the whole half of the power goes to the normal conductor and half to the superconductor. So it serves as a very nice way of controlling the temperature of the electrons in these conductors. One thing I forgot to say is that there's a kind of a hierarchy of timescales in this system. So electrons talk to these phonons at very slow rate. So the typical relaxation time is like tens or hundreds of microseconds, whereas the electron-electron interaction within these conductors is of the order of nanosecond, meaning that whatever perturbation you do to the electron system, for example, by Joule heating, the temperature in this electrode is quite uniform, and then it changes determined by the contact to the phonon bath, but much slower. So here is our first kind of or archetypal measurement of this kind of effect. This is exactly like the Johnson-Nyquist setup that I was showing to you. So what we have is that we have these two resistors here, in this case at the distance of maybe 30 micrometers from each other. And they both have several of these probes and control electrodes for doing the experiment in the way that I was explaining. And now what we can do is that if you apply the voltage across one of the contacts here, then you can see that the temperature the local temperature, which is the blue one here, is first it's decreasing because of this effect of cooling. And when you go further in the voltage above this gap voltage, then you start to heat the thing up. But surprisingly, or not surprisingly anymore, of course, but a little bit interestingly at that time, of course, was that even though these are connected with very weakly conducting leads, they are pure aluminum superconducting leads, which really don't, they are exponentially suppressed in terms of the thermal conductance. You still see that the other end at 30 micrometer distance is also following this. So it's cooling down and then heating up. And the lower you go in temperature, the better they follow each other. So they talk to each other very well at low temperatures, and this is exactly due to this photonic heat coupling. And if you really compare this change of temperature, for example, at this optimum point here, you see that it is this ratio here is approaching 1, and it's actually very close to what you would model by assuming that there is a quantum of thermal conductance. This has been repeated in other setups. For example, one can really have distant cooling at the distance of even basically physical distance of millimeters, but even with this line length, which can be up to 1 meter. So it's an effect where you can really provide remote cooling of the system. Then one can also have setups where you are really controlling this, let's say this small r that we had in the first expression there, controllably. So let's say that we have 2 of these resistors, and then you put some kind of a intermediate impedance in between them. And typically we want to put there some reactive impedance so that it doesn't really have extra dissipation, but it modulates the impedance of the whole circuit. And what we often do is that we put the superconducting squids, which are nothing but, they are, in this respect, they are nothing but parallel LC resonators, which then, where you can by magnetic flux tune the inductance of this LC resonator. So what you do effectively is that by changing by magnetic flux, you can change the effective impedance between these two resistances, and this way you can see that this heat transport by these microwave photons here is modulated, as shown here on the right hand side. So if you do this at very high temperature, then what happens is high temperature for us in this case means something like close to 200 milliK. You can see that when you put heat here, the temperature modulation of the other one, or even this first one, is quite vanishing, because there's electron-phonon coupling having a high power in temperature as for the conductance is really shunting the system totally. But when you go to a lower temperature, then the electron-phonon coupling ceases to be the dominant path for heat transport, and you start to transport heat via the other resistor as well, because of this photonic heat transport here. So at the lowest temperature, you can see that the temperature is modulated as a function of the flux, because this inductance here is really flux dependent with a period of 1 flux quantum for a superconductor. Recent experiments, which are in fact still very much ongoing, are shown here. So we are repeating essentially the same experiment, but now in the system where these 2 resistors here, I mean, in the earlier experiments, they were made quite small, and then this LC model with the chosen junction worked very well. But the idea is that when you make a very resistive environment here, we go from few ohms up to tens of kilo ohms here. In this case, this environment here starts to be it starts to influence the tunneling because of the exchange of heat of this tunneling process with the resistors in environment. So at the moment, what we are trying to see is how is this picture breaking down when you go to the area where dynamic Coulomb blockade due to this exchange of energy is affecting these effects. One can also do the same same type of experiments by not using the magnetic flux control, but you can also do it by applying gate voltage to a system. So for example, to a single electron transistor, you can change this kind of impedance of the intermediate system by applying a gate voltage, which then effectively has the same effect on magnetic flux. It's kind of a dual effect. And also in this kind of a system, we can see the similar modulation of heat transport by the control parameter of these photons. So let me now go to the more kind of, how to say, maybe even modern experiments, in the sense that we are trying to use superconducting qubits as elements in this circuit to modulate and to control the heat transport in the system. And for this, we have currently quite a nice setup in our own laboratory, because we have different types of superconducting qubits at our disposal. So we started with so-called transmon qubits, which are more or less harmonic oscillators. So their unharmonicity is very weak, and from the point of view of thermal experiments, you can almost assume that they are ideal harmonic oscillators. But on the other hand, there's also a choice to use either so-called flux qubits, where the unharmonicity of the system is much stronger, so you are coming closer to a true two-level system. Similarly, you can use so-called charge qubits, where the charge degree of freedom is the important ingredient. And there also you can have very unharmonic spectrum between the levels of the qubit. So this is kind of the palette that we have for different types of experiments now. And I will start with the first experiment, which was done a few years ago in our group. So this is a setup which we would call a heat valve or heat switch, and in spirit it's quite close to the one that I was showing as the early experiment, in a sense that what we have here is that we have a standard transmon type qubit here in the center, which can now be where the level spacing of the qubit can be tuned by the magnetic flux due to this presence of the squid here. And now this squid here, this superconducting qubit here is connected to two harmonic oscillators. Let's say they are harmonic oscillators. They are two different coplanar wave resonators, superconducting resonators, which are then terminated by these heat baths, which are on this scale quite small. They are seen here as the resistors here. And again, we can just probe and control the temperatures of the two. So now the idea is that if you put this qubit here, how does the heat transport between the two ends get modulated? And in this experiment, the simplest picture is naturally, as already kind of clear from the earlier thing, is that when you tune the inductance, or let's say the qubit here, then the level spacing of the qubit is changing, and at the moment when this separation or energy of the qubit becomes equal to the two resonators, which in this experiment are nominally equal, then you can have a path for photons to travel from one end to the other due to this resonance condition, and we are going to get photons down the road here. So in this kind of experiment, by the way, the number of photons that we are transmitting is like about at the minimum it's like 1 million photons per second. So, and this is what in fact happened in the experiment, in the first experiments, when we had this qubit here and we had connected it to the resonator, which is in fact quite strongly coupled to the reservoir. So when we made this resonator quite dissipative, let's say having a low quality factor, then what happens is that this reservoir plus resonator, they act as a structured environment for the qubit. And it's quite simple to do the theoretical analysis of this system. So finding the transition rates of the qubit due to this kind of weak coupling golden rule rate expressions for the qubit. And what one finds out that in this case, the power between the two resistors is given by this Lorentzian filtered expression, where the two populations of the two resonators here appear as a difference here in the numerator, and the quality factor appears there. And naturally, you need to hit the resonance. You need to hit the qubit with the resonator, and this happens again twice in each flux period. And this is what we see in the experiment. You can see that that at different bath temperatures, indicated by these different colors here in the lines, you can see that the heat current, which typically is of the order of femtowatt, you can see that it is modulated exactly in the way that we would get from this simple model. So here the only fitting parameter for the experiment was that the quality factor we couldn't measure in situ for this, but it's in a reasonable range taking the system that we have. And we can also cool the other end. So if we apply this small bias voltage to the control contacts here, we cool the local resistance, and we can also cool the distant resistor by the same effect as before. So then there's another regime which we would call a global regime, where now instead of having a strong coupling to the, not strong, but let's say it's a question about the hierarchy of the coupling. So we have gamma and G here. If you now make this gamma here weaker than the inter-system coupling G here, the coupling between the qubit and the resonator, then in this case, what you can imagine is that you have kind of the combined or hybrid quantum system here, which then talks to bare baths at the left and right. And in this case, it's also, I mean, it's possible to characterize this system. First of all, we did that by spectroscopy, by making this coupling, in fact, vanishingly small by removing these resistors here and looking at the levels of this three oscillator system. And what we found out is that there are the different levels of this multi system, where the energies are from the spectroscopy are given by this as shown here. Now we can model it very simply by assuming that the Hamiltonian is composed of the bare occupations of the qubit and the resonators, and then the couplings between the different elements in the system. And this we could all then extract from this diagnostic measurement and could determine them quite accurately. So putting those together, we can then model the system, find the power in this kind of the global system, and now in the experiment what we saw was in fact quite less obvious or less intuitive pattern of the flux modulation of the heat transported between these two resistors in this regime where this intercoupling here is strong enough. And this is also revealed by the model that we were writing for the system. So we have kind of two different extreme behaviors of this system. And more recently, what we have been doing is we have been trying to understand how the crossover happens between these two regimes. So what one can do, in fact, in theory, is that we can assume. I mean, the simplest scenario here is that they assume that we have a low temperature, essentially a zero temperature oscillator bath, which is then coupled to this combined element of a qubit and one resonator, and we can see how the system, how this qubit or this whole system here decays to the ground state from the initial state. And we can see that initially if this coupling here is weak, this is just doing coherent oscillations here. And when you start to increase this coupling here, you can see that the system decays from the eigenstates more or less exponentially, whereas still you can see that there are oscillations between the two elements. And until you go to the extreme case when this coupling to the bath is strong, and then you can see that the qubit as such is decaying exponentially, and the resonator is essentially all the time staying at the low temperature together with the bath. So one can model this we did this by solving directly the Schrödinger equation for about 1 million oscillators in the bath. Okay, so then let me go next to the a little bit maybe a little bit more quantum again, by taking the system which is not so symmetric as the previous system. So one interesting question is can heat be rectified? And of course there are already many experiments in more kind of classical systems, and recently there have been quite a lot of theories for quantum rectifiers, like one could say that the first seminal one is the spin boson model from Segal and Nitsan, which in fact could be applied to our systems quite nicely. So the ideal rectification naturally is that you set a temperature difference like we do, and you look at the heat current through your system, and then what you do is you just reverse the temperature bias and measure again the heat current. And if these two heat currents are not the same, then you tell that you have rectification. So in the previous experiment and in similar ones, we naturally have no rectification because the system is fully symmetric. But now, if you make okay, I will. This is essentially a recap of this spin boson model, where you can do it in a very simple way by just putting a two-level system here and having the rates that you get from the golden rule for this kind of a system of, for example, electrons coupled to a qubit, and then you will find out that there's a rectification, provided the two couplings here are not the same. And the other important thing is that this is two-level system. If it was not two-level system but the harmonic oscillator, you wouldn't have this rectification effect. So what we do in the experiment is that we make these couplings different to the two baths. And in this first experiment, what was done was that one of the resonators has much lower frequency than the other. So in practice, it was 3 gigahertz and 7 gigahertz. And the intermediate qubit here, we tried to make it a little bit more unharmonic than the previous one, but still we are using the transmon qubit where the unharmonicity is quite weak. Despite this, we could indeed observe some first signatures of this kind of wireless quantum rectifier by applying this this principle of putting a temperature bias in one direction, measuring the forward heat current, and then reversing the temperature bias and measuring it again. So first of all, there's some overall difference in the forward reverse directions, which can be partly attributed to the inaccuracies maybe in the calibration of this thermal response of these thermometers on the two ends. But you can see very clearly that these patterns in the two directions are totally of different shape, which means that inevitably you have a rectification here. So if we just subtract this overall difference between the two, we can see that this rectification factor here modulates such that we have about 10% rectification at certain positions of flux of this system. This system is very difficult to model precisely, at least has turned out to be quite difficult to model for us, and currently we are trying to do experiments which would be resembling more this initial spin boson system by getting rid of these resonators and in the future also changing the qubit to more unharmonic one. Of course, I mentioned now, before I go to the second part in this, I mentioned that we also are, at the moment, we are working on trying to realize real heat engines with this. So instead of doing what I have been talking now all the time, doing a passive heat transport experiment through this quantum system, we try to make active refrigerators by applying a time-dependent fields on this qubit. By this we can do work on this working substance here, and this way we can hopefully carry heat from the cold bath to the hot bath. So this experiment is not yet, we don't have yet results on this, but the interesting things there are that one can, I mean, of course, one can model this system quite in a simple way. You can just, what happens is that if you change this flux, for example, in a qubit such that the qubit is in resonance alternately between the left of it, between the right resonator and then to the left resonator, then what happens is that you are carrying heat from the system on the right, which has a lower frequency, to the system on the left, which has a higher frequency. So this is very simple to prove on few lines, just looking at the assuming that it is a quasi-static process, so that the system is always thermalizing to the qubit is always thermalizing to each bath when it's in contact to it. And this would lead to the cooling power, so the power which is transferred, and the interesting thing would be to see that there are some quantum signatures in this power when the qubit in fact is not running anymore quasi-statically, but it starts to make coherent oscillations, and then you can have like Landau's energy physics there as well. Okay, but let me go now to the second part, which is calorimetry here. So it is this is something what we are in fact aiming at is to measure now not only. So these were like the first experiments were like bolometric experiments. We are looking at the steady state heat currents, but now what we would like to see is that if you have a input to this system, which is composed, for example, of the energy of a single microwave photon, can we detect that by a thermometer which is fast enough, for instance? So this is kind of our current solution of the calorimeter. So it is a small piece of metal which is connected to the thermometer, which again is a superconductor connected by a tunnel barrier to this thing, and then we run this in kind of a fast measurement, as there was a question about this. I will show it very briefly what I mean in a minute. So what is the limiting factor in doing such calorimetry is that the temperature, effective temperature of such a bath is always affected by the coupling to the in our case mainly to the phonon bath. So there's heat current noise, which is kind of from the fluctuation dissipation theorem for the heat current. It is proportional to the T squared, and then naturally to the thermal conductance between the two. So in the low frequency regime, the heat current and the temperature difference are related directly, and you would expect that the effective temperature of this kind of a detector here is fluctuating with this according to this formula here. And then, of course, if you integrate at all frequencies here, you will find out that the RMS noise of this effective temperature is KT squared over the heat capacity of the system. So our aim is to measure an absorber, which is this metallic one, and look at its temperature in this temporal fashion. So we have a thermometer which ideally has a time resolution of microsecond. In the first experiment, we used only like 10 kilohertz time resolution in this measurement, and this thermometer in this case is close to what I showed before, but we found out that the type of the thermometer we are using is not maybe the best one in the lowest temperatures, and we transformed it into this kind of a proximity enhanced tunnel probe here, where the zero bias conductance of the junction here is then affected by the proximity superconductivity of the normal metal. This way we can make a measurement at non-biased conditions at zero bias, and this makes the measurement much less invasive, and we can do measurements down to 10 or 20 millikelvin temperatures, which is very helpful from this point of view. So now the aim in this experiment is to measure the absorption of single microwave photons by this thermometer in real time, and based on our preliminary experiments, which were indeed they were limited exactly by this FDT of temperature. We can predict what sort of temperature fluctuations we would have as determining the signal to noise ratio in this experiment. Now, taking a typical energy of a qubit, which is somewhere around 1 Kelvin at maximum, we can predict that there is a window so that the temperature change of this probe will be exceeding the noise due to the coupling to the phonon bath. So if this will work, I mean, it's still a work in progress. This will, of course, open a lot of opportunities of doing stochastic thermodynamics for a purely quantum system. So our idea is, or our goal is naturally that we start to drive these qubits. We measure the temperature traces of these absorbers here, and based on the history, or let's say this decay statistics of the qubit here, we can then check, for example, different types of fluctuation relations that are related to this. It seems, though, that this measurement here is not. I mean, I showed you that ideally you can have a possibility to measure this single microwave quanta by a single thermometer, as I showed here. But quite recently, we were applying the same technique as I showed about this local studies. We use this oscillator bath technique to see what happens if we connect two of such absorbers at the end of our resonator here. So when the qubit is decaying, we can have a little bit maybe a counterintuitive situation that we see that the energy of this quantum, it is split into these two different resonators. These two different absorbers at the end of this resonator. And this will give us an opportunity to really enhance the signal to noise ratio of such a measurement. So if measuring single thermometers, you have these blue traces here. If you do the measurement of cross correlation, for example, measure the time derivatives of the two temperatures, you will really get an enormous enhancement in signal to noise ratio. So this is something that we have now ongoing in the experiment. Okay, so I think in the interest of time, I will skip this part here, or maybe I will say that one thing concerning the heat transport, which we are quite interested in, is of course the noise in this heat transport between these resistors, and the basic idea. The basic idea there is that our basic interest there is to potentially measure, first of all, to measure the noise due to this photonic heat transport here, but also to measure the quantum noise of that. And there are some interesting questions there. What is the spectrum of this, or let's say what is the frequency dependence of the heat current noise? And this is seen in several works that there's the heat current noise by different carriers. It follows more or less what one would expect from the standard fluctuation dissipation theorem for frequency dependent fluctuation dissipation theorem. But one can see that there's always a term which survives even down to the lowest temperature. So this is an interesting thing that we would like to, of course, see, but in this experiment but it's the frequency where you would see this is quite high. So what we proposed in the recent work here is to down convert this by modulating this impedance between these two things. Okay, so let me go to the last part. How am I doing with time? Still a few minutes.
Go ahead.
Okay. So I will talk about a little bit more classical effect at the end of the talk, about still related to heat transport naturally. So we call it frequency to power conversion. And for this, I would like to start by just recapping on what the system is here. So we are now turning our attention to essentially to single electron transistors. So suppose you have a standard single electron transistor. I think most of you at least have an idea how it behaves. So in terms of the electrical current transport through a single electron transistor, what you have is that you have a gate dependent current which is periodic in the sense that as soon as you put a displacement charge which is equal to 1 electron, then you get to the next period and so forth. So you have current voltage characteristics which depend both on the gate voltage on this system and then on the bias voltage across the system, so that you will have these what famous Coulomb diamonds here, where the system does not transport charge at all at the low temperatures. A variation of this is a system which is very close to what I showed for these thermal experiments earlier, is that you make a similar single electron transistor, but now such that the central conductor here, let's say the island here, is made out of the normal metal, whereas the leads are made out of a superconductor. In this case, what you have is that the charge transport is forbidden at low bias voltages, and you will see that these Coulomb diamonds here extend on top of each other, such that you will have periods. You will have bias range in around 0 volts, where the electrical transport is forbidden at any gate voltage, and this provides you the possibility to make what is called a single electron turnstile, where by varying the gate voltage periodically, just simply varying this gate voltage periodically, you can transport a single electron into the island, out of the island in each period of time. And this produces you a current through the system if you drive this gate at the frequency of F, which gives you a current which is strictly proportional to your frequency. Of course, there are some errors there, but very closely following the relation where current in this first plateau here, current plateau is given by E times F. And now if you increase the gate amplitude, you can get many charges running through this system. So this is kind of a candidate, has been candidate for electrical metrology. But what I wanted to show here is a very fresh result, which is that you can also create an interesting device, which could be a standard for power. So for watt, for small powers. So suppose you take the same device. So okay, you should have a look. Here is our similar single electron transistor in the center, and then you put a alternating gate voltage here, which is injecting the electrons to the superconductor. Now all these electrons here, which are injected, they are injected at the gap voltage here, and they produce an excitation to the superconductor equal to the energy gap of this superconductor. The electrons then, these excitations, they diffuse to an absorber or to a bolometer here, whose temperature is rising due to the injection of these single electrons to the superconductor. Each of these electrons carry an energy delta. So now if you again modulate this gate voltage at the frequency F, what you expect is that in fact, because this is a symmetric effect, in each half period, you create an excitation in the superconductor of value delta. So you will get like 2 times delta F power to be injected from this system. And this is a system which works also at 0 bias voltage. You don't have to bias it at all. You can get this. And then if you measure a similar characteristics as for electrical current, but now just for power, so this corresponds to 0 electrical current, there's a power with no net electrical current, you can see that the power as a function of the gate amplitude and gate offsets is giving you plateaus of multiples of this superconducting energy gap times the frequency. So this could be, I mean, these powers are of the order of femtowatts. So this could serve as a standard for what. Of course, the accuracy at the moment is still only on the level of several percent. So this is a work that was done just very recently, and it will be published today, in fact. So that was essentially all I wanted to say. So this work here is done in my group. So many of the experiments I showed and also the theory were done together with Bayan Karimi, who's a finishing PhD student, and with several other PhD students and postdocs here which have been participating. So, for example, this heat valve experiment was done by Alberto Rondoni mainly, and this rectifier experiment by Jordan Senior and colleagues. So I think I finished here. Thank you for your attention.
Thank you, Jukka. So are there questions? I've actually got a question myself. Maybe I can start. You can start with my question. So when you consider the qubit harmonic oscillator connected to an external bath, you showed the result for two regimes. One which was strongly coupled, and one was maybe it's next one. Yeah, this one, and then you show.
Yeah, I mean, I did put them on the same slide, but I mean, these are like the two regimes that you are talking about. Exactly.
And maybe I didn't get it. So when you say a strong coupling, what do you mean? What is strong coupled to what?
Absolutely. So nothing is coupled strongly. In fact, it is just a question of the relative strengths of these two different couplings here. So in case, I mean, all this modeling is done just using the standard Lindblad type analysis. So you don't need any strong coupling there. So it is just when this G as compared to gamma is large, so to say, then you have this picture. The system behaves like a combined system, which is decaying to bare heat baths. Whereas in the other regime, in practice, when you decrease the quality factor of these resonators, meaning that this gamma is here larger, then you come to this other regime. So then you have a qubit that sees this kind of a structured environment composed, or let's say this filtered environment via the resonator.
Okay.
So that's and this picture seems to work well.
Yeah, I was a bit confused by local versus global.
Right.
Approach. Yeah. That's clear. Thank you. Yeah. More question?
Yes, I have maybe a couple of questions concerning this valve, and then you went to the heat rectifier. So the rectification power that you get, it's already, I guess, for experiments is quite good. It's like 10% is not bad.
Yes.
Can you increase that or decrease? So I guess this is controlled by the couplings, these gammas that you were
absolutely. I mean,
and how large in rectification power you can go? How high?
Absolutely. I think this, I shouldn't say that I'm ashamed that it's only 10%, but it can be much larger, because the choices that we made here in the first experiment, they were just dictated by our aim to use the transmon qubit for other purposes here. So, what matters is naturally the ratio of the couplings to the left and right, and also this unharmonist here. And the transmon qubit, as I said at some point, is that it's the worst choice from the point of view of having a nonlinear system, because the unharmonicity is only of the level of a few percent. So let's say the ratio of the energy separations of the ground state, first excited state to the second excited state, they differ only by a few percent. So this means that it's very weakly unharmonic system. So I'm kind of 100% convinced that we can get much closer to this kind of a setup by applying another type of a qubit there. So flux qubit is a choice, charge qubit is another choice. Plus we can control these couplings also quite well. We can make them. I mean, eventually this ratio of the two couplings will then determine in the limit of two-level system will limit or give the rectification ratio. So there's I think we can get easily much higher rectification. I don't know exact number. It will depend again on many things, but ideally you can get very large rectification factors here.
That's very nice. And I have a second question. So all these systems, when you measure heat transport, they are zero-dimensional, right?
Yes, and it depends on from which point of view. Yeah, so exactly, you can model them like zero-dimensional absorbers, for example.
Yes.
From the point of view that I mean there are no temperature gradients inside them. Of course they are not zero-dimensional from the point of view of electron gas, for instance, because the Fermi wavelength of the electrons is in metals is just much smaller than the size of the islands itself.
Yeah. Yes, exactly. But have you or could you consider extended systems like quasi-one-dimensional, like for instance what people do with carbon nanotubes, and maybe able to measure the temperature locally along the system? Yeah.
So of course one can get yes. So in fact, it's even it depends also on the choice. I mean, you can get temperature gradients in these wires easily. For example, in this experiment that I showed. Wait. Now I should go back. Sorry, I'm just. There was one of the measurements which I didn't really explain in depth. It's this experiment where we try to use the highly resistive environment for this photonic heat transport. There, these resistors are made out of chromium, which has like orders of magnitude larger resistivity than copper that we usually use. So there, in fact, one of the problems from this experiment point of view is that you immediately create temperature gradients across the resistor. So it is possible to do that, definitely.
Very nice.
And still, I mean, the coupling to the phonon path is always very weak. So then it's an interplay whether you have a gradient or not.
Very nice talk, Jukka. Thank you.
Yeah. Thank you.
So, are there more questions? Okay. Seems there are no more questions. So, yeah. Well, thank you again, Jukka.
Thank you.
And